Hey there guys, uh, this is just a bit of a lowdown on what Lab 7 of EP228 kind of looks like. Um, it's just a lot of function writing. It's not too bad. So the very first question asks us to derive rotation matrices for a three-dimensional system. And if you Google this, sorry, I forgot to do that earlier. It will look something like this. And so you might be wondering how you can derive that. Well, what you have to look at is we're going to rotate first around the x-axis. So what we want to do is we want to pretend that in our, if you use right hand rule, normally your index finger is your x-axis, the outstretched fingers are your y-axis, and your thumb pointing up is your z-axis. We're going to change this so that your x-axis is pointing up, and then you have your z and y axes, and you're rotating around x. So your theta is really just your z and y axes. So if we go back to the notes that Pasha put online, you can see that we already are given how to derive a two-dimensional rotation matrix, and it's just this guy here. Well, I guess this one, R. R is our rotation matrix. So we can, since we know that x is going to stay constant because you're rotating around x, there's no change in x, we can all of a sudden look at this and we can see, oh, our x-axis and x components are not changing. And this system is just, this is one unit vector in the x direction, 1, 0, 0. And then we have, so x, y, and z. It's one unit vector, another unit vector, and another unit vector. These unit vectors don't have any x components, so they always stay 0. You can do the same for y, where now y is your upward axis, and you're just rotating z and x. So the y components of each unit vector stay 0, and of course the y unit vector is constant. Then again for z. So this is and it's the same rotation matrix, same order, you just place them in different spots because of the axes that you're rotating. So that is basically it for the first question, question 1. For question 2, we go into MATLAB, and we have been given two functions, setup 3D plot, which is literally just gives you a 3D figure. So if we do setup 3D plot, and we put figure 1, and my computer is very slow, so apologies. There you go. That's the kind of figure you should get. Now we want to plot. We're given a second function, plot polygon faces, which takes a vertice matrix and an F matrix, or our face matrix. So, for example, I don't have it up. Well, let's say we'll use the example in the notes, or in the assignment, where our vertice is, the vertices go in the columns. So, of course, you have one point at 0, 0, 0, right? That's your origin. And then you have another point at 1, 0, 0, so one unit in the x direction, if you can think of it that way. and so that's another vertice. So you can imagine there's a line along the x-axis connecting your origin and the next vertice. Then 1, 1, 0, that's 1 in the x, 1 in the y direction. So that's kind of just out in the middle of your xy plane. And then you have a fourth vertice, which is 0, 1, 0, which is 1 unit in the y direction. And if you plot these as they're given to you, you'll get a xy plane face of a cube. And F is just a matrix that tells you like which points get connected. So say this 0, 0, 0, which is your origin, that's point 1. So column 1 is point 1. And to make a face, you want point 1 to be connected to point 2, to be connected to point 3, to be connected to point 4. So that creates a cube, or a square. So now we can use our plot polygon faces using V and F. And you can see that we have this little square. So let's say we want to create a second face, and let's put it so that it's facing outward this way. So kind of towards us. If we rotate this edge, let's put a face on this edge. So if we are going to put it on this edge, let's call the corner that's going to be at the top here, let's call that point 5. Let's call the corner that's going to be over here point 6. So now our vertice matrix is the same as before, but now we have 2 more points. So now we're going to have 1 or 0, 0, 1 because this is our origin. So we're going in the z direction, only 1 unit, and this one is 1 in the x, 1 in the z. So I just have to remember that. So it's going to be 0, 1 as your added top columns if this is 5 and this is 6. Then we'll do 0, 0, 1, 1, 0, 0. There are no new y components. And then for our z components, we have 0, 0, 0, 0 as before, but now we have 1 and 1. F we do 1, 2, 3, 4, 5, and 6. Now if we set up a new figure, get rid of this one, and we plot the polygon faces. Ooh, I chose the wrong edge. Sorry. Yes, I very much chose the wrong edge. I got my orientation messed up, but you can create a cube by, you can draw it out on paper too. And just label each vertice as point 1, 2, 3, 4, 5, 6, 7, all the way through 8. You should only have 8 vertices. So you'll have an 8 by 3 matrix, or 3 by 8, sorry, 3 columns, or 3 rows, 8 columns. And then your F matrix will have 6 columns. It'll be a 4 by 6 matrix because you have 6 faces. Each F column represents a face. So apologies that I can't really demonstrate that one better. I don't have my drawings scanned or anything, so I can't really show you what I mean. If you have questions, you can email me. So the third question is we want to make a translate function, And this ends up being really, really simple. So what we can do I can't remember how to zoom in. But we have our function translate 3D, which takes in our vertice matrix. So A is just this V down here, and X distance that we want it to move, a Y distance that we want it to move, and a Z distance that we want it to move. So this is just taking the size of A so that we can deal with its rows and columns. So for this first for loop deals with the X components. So first row, different columns every time. This for loop goes through every column and changes the first row element of each column by adding the X distance, because that's your X component of the vertice, right? So if we want to move it by 1 and we put X distance of 1, then it's going to take each X component, so the top component of each column, and add that X distance. And then you can declare your old matrix to be V. You could also put this as B. I didn't feel like doing it. You do that 3 times for each row. So you do it again for your J column, which is your Y components. And be sure to say that it's the second row. This is very important, because if you leave it as a 1, you're going to change your X components and nothing else over and over and over again. And again, for your Z, and you just make sure you have your third row. Then we just say B equals A, and that's what we're returning. So that's the translate function. It's very straightforward. You just need 3 for loops that moves each element of a row by a certain amount that you input up here. The next part, and testing it, you can just run it with when you've made your cube. You can run that, and you can see up here there's a tool. If you hover over it, it should say data cursor, and you can click on the vertices of your cube and it'll give you data points. So that's a way to check if it's moved. The next one was scale 3D, and this is identical to the translate, except that instead of a plus, you're multiplying. So it's literally just changing this plus to a multiply. That's it. So you can also test this by seeing if you multiply each x point by 2, your cube will change shape, obviously, and you can check with the vertice with the data checker as well. The next, number 5, is rotate. 3 rotation functions, and these might seem really scary to start, but if you remember the rotation matrices we made for 3D, you can actually just build those as R. So rotate takes in our vertice matrix and a theta in degrees that we want to rotate the matrix by. So theta is always in degrees, so that means that when we put a cos or a sine, we obviously have to put cos d or sine d theta. Otherwise we're dealing in radians and we will get a very different answer. So our matrix for x, if we remember, was 1, 0, 0, 0 cosine theta, negative sine theta, 0 sine theta, cos theta. So we literally just write that in, remembering to put sine d theta, cos d theta. And then if we look in the notes that Pasha gave us, we can see that our new rotated matrix, or rotated vector, equals our rotation matrix times our old matrix. So we can just do that. We can say that B, our returned vector, vector matrix, is going to be our rotation matrix times our vertice matrix. And that's it for X. You do it again for Y, but remembering to put your Y matrix, Y rotation matrix in instead. Multiply R times A. Exactly the same thing for Z. And just remembering that theta is always in degrees. So now that we've built all of these other functions, rotate, translate, scale, we can now start looking at how to do question 6, which is to build a water molecule. So we were given a function, unit sphere, and this creates a sphere of a unit radius, so 1. And I just built a small function that creates a consistent water molecule, and it returns the oxygen base, like vertice matrix. It returns the hydrogen vertice matrix, the second hydrogen vertice matrix, which I'll get to explaining, and V faces. And V faces is just your like F matrix, and it's the same for all of the spheres. So first things off, we create this unit sphere with just returning V and V faces, because we're going to alter V as, continuously as we build everything. So our VO, according to what is given to us in the question, it says that the molecule is 1.4 times bigger than the H molecules, which means that we need to scale the whole thing by 1.4, and we have to make sure that we scale the X, Y, and Z components. So we call our scale 3D function, and we pull in this V, which is just the vertice matrix, and we scale it by 1.4 for X, Y, and Z. That is our oxygen. That's our oxygen atom or molecule. Oh boy. No, they call it molecule in the notes, so we'll go with that. Our hydrogen molecule is very similar. It says that each H is 1.4 times the radius of the given unit sphere. That's the bond, or sorry, the bond length is 1.4 times the radius of the given unit sphere. So that means that we need to move the center of our hydrogen molecule 1.4 times out. So, or 1.4 units out. So that's what this is. And I just moved mine along the x-axis. You could move yours along the y or z. It doesn't make a difference. So I move mine along the x, and then I know that I need a second hydrogen. So I create H2, VH2, but this time I need to rotate it because the angle between the centers of the H molecules is 107 degrees. So I rotate mine around the y-axis, because that was what worked for me. I found that it moved 107 degrees when I rotated around the y. So I said that my VH is going to be rotated 107 degrees, and that'll be assigned to a new vertice matrix. So now I set up a new 3D plot. I plot all three unit circles or unit spheres, which is VO, VH, and V2. So when we run this, we get this guy. So pretty. And you can see that this bond angle is 107 degrees. And there's the large O molecule and the two hydrogen molecules. So finally, we need to make it rotate around each axis 360 degrees. So I just wrote a script, not a function, for this one. And I start by making my plot in figure 1. I call my create water molecule, which was just this guy right here, which I just explained. And then now for each x, y, and z, I rotate. So this for loop rotates around the x-axis first. So I do VO, my oxygen molecule, I need to rotate it 1 degree around the x-axis. Same for H and H2. And I do this until I is 360. So until it increases it by 1 degree 360 times. I need to set up a new plot each time so that it doesn't draw over itself, and it also doesn't give you 1,000 plots, which is quite literally what would happen if you ran it for all three. And then I use my plot water molecule function, which I have right here, which just basically plots you could put this in, I don't know why I wrote this, but plot polygon faces for VO, VH, and VH2. So you do that, and then you put this draw now underneath so that it will it will output the picture of the graph right after it runs one for loop. So it'll do that, and then setup 3D plot 1 will reset it so this won't be applicable anymore, but it plots the water molecule right away, so there's no lag. But draw now, you need to have that so that you can actually see it rotating. You do the exact same for the y-axis and the z-axis, making sure that these are all 1, and you just count through 360 rotations. And when we run this, you can see that the water molecule, my computer, for some reason, its draw speed is a lot slower. I don't know why, but it will rotate all the way around the x-axis, because we're pretending that this is positive z, positive x, positive y. And now the y-axis. So slow. And finally, the z-axis. So it will go all the way around, and no, except it's still running, so I can't really. I guess we'll watch it. So there you go. So that's how, that's assignment 7, essentially. It's not too complicated once you wrap your head around the vertice and face matrices. The rest should follow pretty quickly. Yeah, if you guys have questions, I don't know if anybody really needs this tutorial this time, but if anybody has questions, let me know, and yeah, just email me and I'll try and help you out or explain better what I did in my functions. So yeah, cheers.